Here's the final video to the lecture intropde. In this video we present section 5.8. In this section we want to prove uniqueness of solutions of the wave equation. And we cannot apply maximum principles, because maximum principles only are valid for PDEs, which ensures that the Hessian cannot be indefinite. So these are exactly the elliptic PDEs and their limiting cases. For example, the parabolic PDEs. Yes, and for this, for such elliptic PDEs and their limiting cases, these methods of theorem 3.13 indeed implies and gives a maximum principle also in these more general situations. However, the maximum principle is not true for hyperbolic PDEs. So we need another method. But there exists, but these energy methods, they indeed imply. So we want to show in this section how we can use energy methods in order to prove uniqueness. Okay, so let's prove the following theorem, which gives us uniqueness in a specific sense. So we have given some domain omega. We fix some domain omega in Rn, and then we look for solutions on omega cross 0 t. Again, on the parabolic cylinder. We call this parabolic cylinder. Okay, but here maybe I should not rephrase. Since parabolic cylinder is related, of course, to parabolic equations, but here we have a hyperbolic equation. Okay, but we look for solutions on this domain, and we assume that we are in a very general situation, so we consider the inhomogeneous wave equation, and we fix initial values. So we fix the values of u for time t equals 0, and in addition we fix it along the boundary. So if we if we have here x1 and here xn and here the time t. So we have here our domain omega in this plane, and then we have we have this boundary along for all times. We have this boundary here. This is the boundary on this time, and along this boundary of omega for all times, and for which we consider the solution, or for which we want to obtain uniqueness, we have to also fix the value of u. And then, so this is similar to the Dirichlet problem. And then we also, of course, fix the initial value of the time derivative of u. And in this situation, we show that we have uniqueness, that has a unique solution. Maybe one should add here on omega times 0 t. Okay, I changed here. I consider now the open interval, because this is since we only allow differentiability in the interior, we have here 0 t, and then we also here have 0 t. Also maybe we include t. Yeah, and then we have only a unique solution for on this domain. Okay, now let's look for the proof. Yeah, the difference of two solutions solves the analogous homogeneous initial value problem. Yeah, with f equal g equal h equals 0. Yeah, of course, since everything is linear, if we have two such solutions, then the right-hand side will vanish. Yeah, for all these conditions. Okay, now we define an energy. For such solutions, we define the energy. Yeah, this is of course positive since it's a square, and this is a sum of squares, so it's also positive. So we have an integral over some positive functions, and this is of course non-negative. Now we calculate the time derivative of the energy. Yeah, so we calculate the time derivative, and then clearly we have here omega doesn't depend on t, so we can put the time derivative inside, and then we get twice second derivative times the first derivative. Yeah, so we get this expression here times this expression. Okay, I reverse this order. This is more clear. So, yeah, if we take the second derivative, so d by dt of du by dt of xt square, yeah, then we get a 2 and du by dt square of xt times du of xt by dt. Yeah, by the chain rule, of course. Yeah, and this 2 cancels with this 1/2, so we get this term, and by the same calculation, if we calculate the derivative of this square, then we get d by dt gradient u of xt times gradient, a scalar product with gradient of u of xt. So we have, and of course, again, a 2. By this 2 here, we get a 2. And as the outer derivative, 2 times this, and then we get this expression. Okay, and now we do a partial integration. And now we do a partial integration. So we look vector field. Yeah, we look for the vector field du by dt of xt times gradient of u of xt. And if we calculate the gradient of this thing, then of course we obtain this term here. Yeah, we obtain this is d by dt gradient u of xt times gradient of u of xt, and we have another term, of course, plus du by dt of xt times Laplacian of u of xt. And now this is now important, yeah, since u of xt vanishes on the boundary, yeah, for all t, for all capital T, until capital T, until capital T, du by dt, of course, vanishes on this boundary. Yeah, here, since u vanishes, also the time derivative vanishes. So this term vanishes on the boundary. So the whole thing vanishes. Yeah. So our vector field here vanishes on the boundary. So we get no boundary terms, and then we can just perform partial integration and transform this term. We only change this term here to minus this term, yeah, since the sum of integrals on the omega, yeah, for fixed t of this plus this vanishes. This is equal to minus the integral of this. So we have, this is just a partial integration, and so we get this term here. Now, but since this difference here is 0, since it solves the homogeneous wave equation, we have that this is 0. So the derivative of this energy is 0. So this means if the energy, since the energy at 0 is 0, yeah, then the energy stays non-zero. Stays 0, since the energy was initially 0, then it stays 0 for all positive times, and this shows that U is constant and vanishes, and then vanishes here on this domain, since it vanishes initially. Okay, of course here we have, this should be only for 0 to t. I changed this. Okay, so now it vanishes on this, and this proves now this theorem. Now, okay, we remark that we get the same conclusion, yeah, if here the partial integration, we did the partial integration with this vector field here, and so this vector field has to vanish on the boundary, or more precisely, this expression times the outer normal has to vanish. Of course, we have two possibilities. Either the first vector vanishes, or the product of the second vector with the outer normal vanishes. Yeah, so if we assume that this vanishes, if we give the normal derivative of u, yeah, instead of fixing u, then the same conclusions holds. Yeah, so this means instead of directly boundary conditions, we could as well take von Neumann boundary conditions of the domain omega. So this means if we fix the normal derivative, then the same conclusions holds. Finally, we want to give a simple proof that the length of the speed of propagation, yeah, is bounded by 1. So what is the theorem which we now want to prove? If u is any solution of, in this time we'll take a solution of the homogeneous wave equation, which is 0 initially. Yeah, so we have here, let me draw a picture. We have here our variables x1 and so on, and here we have time. And then we fix the values at some ball. So we have here some x0, yeah, and we fix the values at some ball at 0. Or maybe I should draw this. And let me try it. Yeah, so we fix at some ball b x0t. Yeah, and then we have some time t0. And and then we have a cone. The cone, which is included by all straight lines with velocity 1, yeah, which go here. So we look for all straight lines with velocity 1 which move in direction of the center of x0 and start at the boundary. Yeah, and so this is this cone here. Yeah, this is the cone that that xt, so the distance of x to x0 is bounded by t0 minus t. Yeah, so these are exactly the domain which is bounded by all straight lines which move with velocity 1 from a point on the boundary of this ball in direction of the center, x0. Yeah, and of course, at t0, they all reach t0, yeah, because the distance to x0 at the boundary point is exactly t0, so they all reach the center at time t equals t0. And then the statement is, if we fix the initial values u and the derivative, so g and h, on this ball, then if we fix this to be 0, so this should vanish just on this ball. Outside it can be arbitrary. Then it vanishes on this cone. Okay, again we use energy methods. Again we define this energy. We define this energy, which is the analogous energy, but this time we only define over this balls which depend on t. So now we want to derive the derivative of this energy. So let us write this formula. This is 1/2. It's the same energy as before, but this time the domain depends on t. Yeah, so these are smaller and smaller balls. And then we have du u by dt of xt square plus gradient u of xt square dnx. And now in order to calculate the derivative d by dt of e of t, we use polar coordinates, yeah, because we want to derive the derivative with respect to t, and for this reason we use polar coordinates. So we rewrite this as integral from 0 to t, and now integral over the boundary of the ball with radius s. Sorry, 0. Yes, t0 minus t. Yes, t0 minus t. And I forgot, we want to calculate the derivative. So d by dt of this expression. And of course, again, du by dt of xt square plus gradient u of xt square, and now integrating over this boundaries of balls. Now, this is what we call polar coordinates. Yeah, we have shown this equality several times. We have used this. Okay, and now we can calculate this derivative. We have two places where it depends on t. This place here, and of course this place. So let's first calculate the derivative here, and then we again obtain this factors 2 for this derivative, which cancels with this. So we may rewrite this again as an integral over this ball, Yeah, for these integrals, we write this again as an integral over these balls. So, because for this term, we have no problem with calculating this. So we have again this expression plus, okay, here a bracket is missing, plus d by dt gradient u of xt times gradient u of xt times dnx over this ball. And now we calculate here the derivative. There we get minus 1/2. No? Here we have a minus, so by inner we have this, and now we should put s equal to, here's missing an ds, of course. S equal to t0 minus t. Yeah, so we get integral over the ball, over the boundary of the ball, t0 minus t, and then we have, of course, this term, du by dt of xt square plus gradient u of xt square, and the whole thing times d sigma of x. And now so now we have this term. And now we again perform here a partial integration as before, as we have done this in the theorem before. So what we get, we again use the vector field, which is just du by dt. Sorry, we only take a partial integration for this term. Yeah, so we use partial divergence theorem. We apply the divergence theorem for the vector field. So xt going over to du by dt of xt times gradient u of xt. Yeah, and then we of course have this term, the divergence of this vector field. We get this term plus, of course, again with Laplacian. Yeah, so we get this term plus Laplacian. So the integral, this integral, has now two contributions. So we get again the integral over this ball, x0 t0 minus t. This term we leave, but now we put out the derivative du by dt of xt, and what remains? It remains du by dt square of xt, again as before, minus Laplacian u of xt. This is the term which was missing here, dnx, but now we obtain another term here inside this. So which term we obtain? So let's now write here the boundary, collect all boundary terms. So plus, let's write plus. Boundary x0 t minus t0, t0 minus t. So t0 minus t. Okay, and what boundary terms we get first? Yeah, we get the boundary terms of this. So this is du by dt times of xt, of course, gradient u of xt, and times outer normal of xt. And then, of course, we have also this term, minus 1/2 minus 1/2 of this term du by dt of xt square minus 1/2 gradient of xt square, and the whole thing, yeah, this here, times d sigma of x. So this means we now have this whole expression here. Yeah, so we have this whole expression, and now let's look at this additional term. Yeah, this initial term vanishes. Yeah, because this solves the homogeneous wave equation. This is 0. So this term vanishes. So it only remains this boundary term. We only have this boundary term. Now, now we want to show that this is negative. And for this, we use the following. We define A. We define a vector A, which is just gradient u of xt, and we define a vector B, yeah, which we define also as a vector du by dt of xt times the normal, the outer normal, of course, of this ball here. So we have these two expressions, and then we clearly have that a minus b square is non-negative. Yeah, so, but this is equal to a square plus b square minus 2a times b. Okay, and what is now a square? A square is gradient u of xt square plus what is b square? This is du by dt of xt, of xt square, and the normal has length 1, so the square of the normal is 1. So we have this term, and minus 2a times b is minus 2 then u du by dt of xt times, so it's exactly this expression here. Yeah? So it's exactly this expression, which, so I write it here, that we have it's gradient u of xt times normal of xt. Okay, so we have this expression. Yeah, this is non-negative, the whole thing. And if we divide this by 2, then we see exactly, we get the negative of this whole expression. If we divide this by 2, yeah, we get the negative of this whole expression. So this implies that e of t d by dt is smaller or equal to 0, yeah, because we integrate over an expression which is non-positive. So this is, the energy is, the derivative is smaller or equal to 0. Yeah? So this implies e t going over to e of t is monotonically decreasing. Yeah, but by our initial values, we have that E0 is 0, clearly, because we fixed, for the energy, we fixed that it is initially 0. So here is the energy. This is 0 and this is 0 initially. So we fixed it that it is 0. And E of t is, of course, non-negative. so monotonically increasing and initially 0, and it stays non-negative. Yeah, so we get E of t is 0 for all t between 0 and t. And this again implies that u is constant, and since it's initially 0, yeah, constant and 0 at t equals 0. So this means u vanishes on the cone. Yeah, so we see indeed a nice application of the divergence theorem, and this energy method shows that that the function really vanishes inside this cone. So whenever it vanishes here, it vanishes inside this cone. We can all apply by the time reversal. Yeah, we get the same argument inside the cone to the past, where we go to the past here, minus t0. Yeah, and by the time reversal. So altogether, we see that if it vanishes in the present for t equals 0 on this ball with the first derivative, then it vanishes on this double cone. Okay, what we have done today we used energy methods in order to prove uniqueness of solutions of the homogeneous of the wave equation. First, we proved it on some domain, and then finally we also applied this energy methods and showed that this length of the speed of propagation is indeed bounded by 1. So now let's we look again what we have shown, what we have done in the whole lecture. First, let us have a look on the last chapter, on the wave equation. Yeah, for the last chapter, we had we followed the following line of arguments. We first proved it, used the factorization of the wave operator into two first-order operators, and then used transport equation and solved for n equals 1 the wave equation. Then we introduced the spherical means, and then we understood that in dimension 3 and later for all odd dimensions, we can derive this Euler-Poisson-Darboux equation, which obey the spherical means, in terms of the one-dimensional wave equation. And then we introduced the so-called method of descent, where this means we considered the initial values in one dimension less, or even later we saw in arbitrary dimensions less, by considering initial values which only depends on some variables. And this means we introduce initial values which do not depend on the other variables. And then we understood that this property also holds for the solution of the corresponding initial values, and by this we obtained the solutions in the lower dimensions. This we call method of descent. By all these formulas, we understood that in even dimensions the speed of propagation has length 1, and in all even dimensions the speed of propagation of solutions of the homogeneous wave equation is bounded by 1. Finally, we understood today how to use Duhamel's principle and derive the solutions of the inhomogeneous wave equations, and we proved by energy methods uniqueness. Altogether, we have now, if we now look again what we have done in the whole lecture. Let's recall what we have done in the whole lecture. So first, we consider first-order PDEs. We started with a simple example, the transport equation and the inhomogeneous transport equation, which became later important also for the wave equation. Then we looked for scalar conservation laws. We understood that by crossing of characteristics we have some problems, and we introduced the notion of weak solutions, and at the end of the first chapter we derived a general method to calculate first solutions of first order PDEs, the so-called method of characteristic. Then we made an intermediate chapter where we introduced general concepts. First we derived the divergence theorem, which became very important later. Then we had a general overview over second order PDEs. Since we understood in the first chapter first order PDEs, we now concentrate in the rest of the lecture to second order PDEs. We gave some example of a PDE with smooth coefficients which has near 1 point no solution at all. So we understand there is no general method for solutions of PDEs, and then we generalized the notions of solutions. This means we had to define more general functions which have derivatives and introduce distributions. And then after this excursion to general concepts, we then solutioned the three main examples. First, the main example of elliptic PDEs, namely the Laplace equation. Then the main example of degenerate elliptic PDEs, namely the heat equation. And then the main example of hyperbolic PDEs. So, thank you for your attention.